Όχι, Adam Babin. Α, το άνοιξα όλοι μπήκαν τώρα. Τι θες?
So I would like to thank everybody for your participation. My name is Konstantinos Dorokodakis. I'm an assistant professor here in Hellenic Mediterranean University. We are very happy. I'm also with my colleague Dr. Irini Koutsouroubi from HMU, who is organizing, coordinating all the events, all the training events, specifically this, that is the first infrachip school. Everybody has received the email from email, so we speak about the hybrid school that will have two different parts. The first part, the online session, is this week. So for all the days, we have planned at least 2 webinars between 11 and 13 CET. And then after the online session is over, we will organize a Moodle test for all the participants. Besides, it's very important that you participate in the online webinar. So we record, let's say, the participation time for all the participants. At the end, applicants that are more active in the school, plus have a good mark in the Moodle test, will be eligible for the second phase, that will be the winter school, an on-site training event here in Crete, in Greece, that will be done in February. So with this, I would like to thank all the speakers, and we start this series of webinars with Professor Babinski from the University of Warsaw. He will speak about 2D materials, an introduction to the whole, let's say, technology and topic of 2D materials and their applications. I think, Irini, you have a short CV from the speaker. So I give the floor to you. Thank you.
Yes. Okay, thank you, Kostas. First of all, I would also like to thank all of our speakers who accepted our and of course all of our participants for their interest in infrachip school. So we will start this session with Professor Adam Babinski. Professor Babinski is a professor at the University of Warsaw, specializing in semiconductor materials and nanostructures. He has co-authored over 150 publications and is particularly interested in the use of Raman scattering to study the properties of 2D materials. So Professor Babinski today will present an introductory 2D materials seminar, and he will provide an introduction to 2D materials focusing on the fundamental properties of transition metal dichalcogenides, and he will discuss their excitonic resonances, lattice dynamics, and how these materials can be used in heterostructures for advanced electronic devices. So, Professor Babinski, thank you again for accepting our invitation, and the floor is yours.
Thank you very much for inviting me. I mean, can you hear me? Because it's always a problem.
Yes.
Yes.
Also, the duration of the
I can hear you.
Good morning once more. I'm really happy to be here and to share with you some basic information about 2D materials. The topic is incredibly broad, so it is very difficult to present all important information during 45 minutes presentation. But I would be trying to focus on some materials and some properties, which from my point of view are the most exciting, but it is far from exhausting the topic. So 2D materials, what does it mean? If you look at Wikipedia, you will find information that 2D materials are materials which are composed of layers of tightly bound atoms bound by covalent forces with very relatively weak van der Waals interactions which keep the layers together. So there is a lot of them. I mean, I think now we are talking about hundreds of materials of that sort of structure, with the most known graphene, of course. You can see that there are also other materials made of one element, which are called like phosphorine, bismuthine, antimony. But there are also other materials, plenty of materials around which share the same structure. And in fact, they are around for years, but it was in 2005 that when Novoselic and Geim, they realized that it is possible to really exfoliate a single layer of those materials. So as a result of their studies on graphene, which is one layer of carbon atoms exfoliated from graphite, then a whole story started with plenty of layered materials. Here in this slide, you can see some of them. The color code tells us which of those materials are stable in ambient conditions, and 2D transition metal dichalcogenides are one of those, and this is because they are stable in ambient conditions. They are so popular in studies, especially in semiconductor physics. But you have many materials from graphene family, so those composed on one element, or other which are shown here as can be made. Look, the paper is already more than 10 years old. Now we know much more about those materials, and we can investigate several of them. From point of view of optical applications, it is crucial to look at the possible band gaps which characterize those materials. So starting from graphene, which is zero gap, which is semi-metal actually, and ending with hexagonal boron nitride, which has a band gap around 6 electron volts, practically a whole range of visible infrared, partially ultraviolet light can be covered with those materials. But of course, it's not that easy. I will show you what are the obstacles, what are the challenges behind those applications. It is even more. Actually, it was in 2013 when the guy realized that having in hand layers of materials, layers of 2D materials, it is possible to create heterostructures, completely artificially created heterostructures of materials which the heterostructures don't exist in nature. But because those layers are kept together by van der Waals interactions, by stacking them and forming the heterostructures, we don't really affect the crystallographic structure much. So it is possible to create several new structures. There is one more thing to be realized here at this stage. If you look at those layers, which can be stacked like Lego boxes, you also can appreciate the possibility of tilting. Each of the layers can be tilted with respect to the other, which opens up the possibility of a new degree of freedom, which we are calling twistronics. So opportunities are endless. As for the properties of those materials, there are several examples you can appreciate in this slide. Of course, semiconducting. I will focus on semiconducting materials because of my particular interest, but you must remember that within just transition metal dichalcogenides, just this particular family of van der Waals materials, 2D or van der Waals materials, we call them both way. We have also metals, we have superconductors, we have structures with particular phases to investigate. And as I told you before, the story is not new. And actually already in 60s, people knew very much about the structure and the properties of bulk materials, bulk transition metal dichalcogenides, which can be exfoliated. Actually, maybe I can go here to show this slide, because it really, I think it is really important to realize that already in 60s, people were using so-called mechanical exfoliation to obtain thin layers of those materials. Thin means several microns. And it was very close to realize that repeating the process, you can end up with one monolayer, but for next 40 years, it was not done this way. So, transition metal dichalcogenides. What about their structure? Two main configurations of atoms in the case of those materials are so-called trigonal prismatic, H, and octahedral T. So during the presentation, you will see that most of the results I will be showing are obtained for this 2H structure, in which metal atom is surrounded by 6 chalcogen atoms, which sit within this prism. Most of materials which crystallize in this form are semiconducting. They have a band gap. On the contrary, if the structure is octahedral, as it's shown here, it is metallic. And those layers, which are kept by very strong covalent bonds, are stacked in material due to the van der Waals interactions. Several structures can be found which, except for 2H and 1T, there is this one.
We don't use LinkedIn. Even in downtown, we don't. Yeah. So then.
And there is some noise.
Actually,
one T prime, which is elongated, actually 1T elongated along one of those direction, and so on. Maybe it's not very important. Variety and characteristic properties of some of them. I would like to show a few slides showing confirming that those TMDs, and especially molybdenum D sulfide, are around for ages or for years. Molybdenite, which is a naturally occurring material, molybdenum ore, and which is molybdenum D sulfide, can be taken from the mines around the world, and actually they have been studying for more than 100 years already. So people were well aware of those properties, but until 21st century, no exfoliated single layer material was obtained. If you would like to squeeze the message about those TMDs in one picture, I think this picture is can be useful, showing that from isolation of first isolation of 2D semiconductor, then realizing of some particular properties of a single layer, we end up with a variety of properties which is rather peculiar, and which open up the possibilities for new applications. How to get the single layer material? One of the ways is liquid exfoliation. If you put that material in some specific solvents and using ultrasound, you can exfoliate and get the single layer. Another way is mechanical exfoliation. This is so-called sticky tape method. Of course, it's now far more advanced than just using the Scotch tape. Using this technique, you can place the sample at a specific position on your substrate. You can create heterostructures. Of course, now it is possible also to grow those materials in standard growth techniques. Important part of the whole story is their thickness determination, and there are several ways to determine the thickness of your sample. One method which is quite often used is just to look at the optical contrast under the optical microscope. If you put one monolayer flake of your material on specially designed substrate, it is important to have the silicon oxide of particular thickness. Then the image under the microscope looks like this. You can see the contrast, the optical contrast between layers of different thickness. It is important to remember that the difference is not really because of the absorption related to one monoflake, but rather to the change in the interference of light reflected from those interlayers. It's just you go out of the interference, then you can see this contrast. After some time, you are able just by looking at through the microscope to see if the flake you have is really one monolayer thick. Of course, the most solid method to find the thickness is atomic force microscope, in which you can see the difference in the thickness of material below, showing that it's really one monolayer thick. And finally, also Raman scattering can give you some information about thickness of your structure, because like in the case of molybdenum disulfide, apparently the energy difference between those fundamental vibrations in plane EG and out of plane A1G, this energy difference strongly depends on the thickness of your sample. So looking at the Raman spectrum, you can judge how thick is your sample, and this works to higher or lower extent also in other materials. So this is the way you can find the thickness of your material. Looking at semiconductor transition metal dicogenides, and these are compounds of molybdenum or tungsten with selen, sulfur, or tellur. You can see that it covers quite some energy range. Difference between the structure of semiconductor 2H or metallic 1T is that, of course, in the case of semiconductor, we have a band gap between energy states, mainly resulted mainly composed of the Z square orbitals of transition metal dicogenide and those other transition metal orbitals. In bulk, you have the energy gap. What is important is that in those materials, light couples very strongly to matter, and you can see characteristic absorption spectra for molybdenum disulfide or molybdenum diselenide at 77, but also at room temperature. And you can realize that also at room temperature, there are very clearly distinguished excitonic peak. Excitons do exist even at room temperature. Then, which means that the exciton binding energy is really high in those materials. I will talk about this later. Another point to remember is that we have two groups of excitons, two excitons A and B, which are related to excitons composed of holes due to spin orbit split valence band. The property which lies at the foundation of the of the interest in those materials is the very strong dependence of the band gap on the layer thickness. Apparently, in the case of semiconductor TMDs, if you go from bulk to monolayer, because of the confinement effect, you transfer the band gap from indirect in bulk. So in this case, maximum valence of valence band is at gamma point. Minimum of conduction band is at the point which is referred as to Q, sometimes A. Doesn't really matter at this. While at monolayer, in the monolayer, the band gap is direct, and the transition, possible direct transition, takes place at the K point of the Brillouin zone, which I will be talking a little bit later. As a result, if you, this is quite famous picture image showing the difference between luminescence from the one monolayer or two monolayer molybdenum D disulfide. So the intensity of the excitonic resonance really incredibly changes when you go from a few to just to one monolayer. This can be also appreciated on this left hand side figure, showing the luminescence and the absorption, measured in terms of photoluminescence excitation. This is this dashed line. So you can see that this transition related to the direct transition from the Kane point does not change its energy very much. What you really see is the effect of the indirect band gap changing a lot from one monolayer to bulk. And also in bulk, of course, if you increase your signal 10,000 times, you can see some luminescence. Yeah, the difference between one monolayer and two monolayer is just 25 times. It's not that great. Okay. So we know that one monolayer TMD is optically active. What is more? And then comes another property of this material. Apparently, if you look at the one monolayer, and in one monolayer, a transition metal dicogenide is composed of the metal atom and those 6 chalcogenide fellows. There is no inversion symmetry in this system, and no inversion symmetry means that because of the strong orbit, the spin orbit interaction, the degeneracy between the two spin projections in each K value are lifted, which means that the properties of electrons from different K values are not the same. The spin projection is different. We can define K and minus K, or K prime, you will see, in those maxima, spin of electrons is opposite, with very important results of this observation. And what are those results? The spin orbit interaction splits both valence band and conduction band. Okay. This splitting appears as a difference between A and B excitons I have shown just before. But the splitting also takes place in the conduction band. Okay, so both valence band and conduction band are split. The crucial point is the order of those minima. Apparently, depending on if we are dealing with molybdenum or tungsten material, there is a difference in this order. What does it mean? This means that in the case of molybdenum material, the lower energy state, excitonic state, combines electron and hole, which can recombine optically. Yeah? Of course, in 1K value, this is related to sigma plus polarization, in the other sigma minus. But anyway, bright exciton which can recombine optically, has lower energy than dark exciton. In so-called darkish material, in materials with tungstens, it's opposite. Bright exciton, combining electron and hole, have higher, which can recombine optically, have higher energy than their dark counterparts. So just one slide recalling what exciton and exciton is. We have a strongly interacting pair of electron and hole, which is free to move through throughout the crystal. And the important part is the energy band, energy bound, which binds the quasi particle. Exciton binding energy is very high. I have shown already it's a few hundreds of millielectronvolts, which allows to see the excitonic luminescence even at room temperature. And this is the comparison of the spectra for several semiconductor materials. We can see the results are from low temperature, but still you can appreciate several facts. First is, of course, we already told that going from telluride, molybdenum ditelluride, up to the tungsten disulfide, you can cover quite a broad energy range. But there is also another feature, very important. If you look at the spectrum from molybdenum diselenide and tungsten diselenide, you will see that the first one is composed of very well distinguished two peaks. One is due to trion and the other is due to neutral exciton. Neutral exciton is a complex of electron and hole. Trion, two electrons and holes, if trion is meeting. While the spectrum of tungsten material is composed of the very broad feature here, which is related to so-called localized states. Apparently, the story behind this is also very interesting, but still the spectrum looks completely different. And why it is so? If we look at the energy structure in both cases, dark or darkish, how we call it now, or bright, as I told you, in the bright material, bright exciton has lower energy. In the darkish material, the lowest energy exciton does not recombine. Okay, so if we look at the temperature dependence of luminescence from molybdenum diselenide, the bright material, by increasing temperature, you start to populate thermally more and more dark excitons, which means that the intensity decreases as a function of temperature, except for this part of the highest energies, which is related to another effect. While if you look at the tungsten material, it's opposite. Apparently, what you can see is that the photoluminescence intensity increases as a function of temperature. Why it is so? Because with higher and higher temperature, you start to populate optically active exciton, and the intensity of recombination of the bright exciton in this darkish material increases. So this is how it works. Then there are more things to consider, because if we look at the tryon in a monolayer of this darkish material, apparently there are two possibilities of putting an extra electron in this complex. Both electrons can occupy minima of the conduction band in the same value, K+. And of course, the recombination takes place between those two particles. As we told, only this is optically active. Okay, but the third electron can be also placed in the other valley. Yeah, because of the interactions between those particles, the energy of the complex is different, and we can see a difference between the energy of so-called singlet tryon and triplet tryon. Singlet is when both electrons occupy the same valley, and the triplet when the electrons are in different values. But it's just the beginning of the story. As we can go further, looking at dark excitons. We already told that the dark exciton is related to spin forbidden, is forbidden by the spin conservation, when electron and hole reside at the same value. But also it is possible to imagine the complex with momentum forbidden, which is momentum forbidden, when the both particles occupy different minima or maxima of the structure. Talking about dark excitons, we are not completely hopeless, because by applying in-plane magnetic field, it is possible to brighten those dark excitons. Magnetic field mixes the dark state with optically active states, resulting in their brightening. So let's look at this spectrum, comparing the emission at 0 at 10 Tesla applied along the plane, and we can realize that this TD state greatly increases its intensity. And what is TD? This is the tryon, which is dark, and it is dark because it results from the combination of electron and hole within the same extremum of the conduction or valence band. And this transition is, of course, forbidden by the spin conservation. It is forbidden at 0 field, but after we switch on magnetic field within the plane, it starts to be visible. So tryon, as the other electron occupies the other minimum in the conduction band. So the story of excitons in those monolayers is really endless, and from time to time people are referring to new quasi-particles, new excitations. But this idea is possible because of some other achievement, and this achievement is the observation that the spectra of those monolayers can be greatly improved if the monolayer itself is put within, is encapsulated, we call it encapsulation, within the layers of within the in between the layers of boron nitride. How it is so? Boron nitride is very, I would say, stiff, very flat. And by putting the layer on this flat structure, it's like, you know, carpet on the floor. If the floor is flat, the carpet will be also flat. And silicon oxide, I don't know if you tried or looked at the image of silicon oxide surface under AFM. It is very rough, resulting in this broadening of the features. So using boron nitride encapsulations, you can see the features with, say, 3 milli-V broadening. Just put on silicon oxide, it's 3 times bigger. This opens up the topic of the effect of environment on the excitons. You can see that there must be a strong effect, and you are right, because the energy structure of excitons strongly depends on the whole structure. Why it is so? Let's get back to our knowledge from the graduate course. We know that electric forces, Coulomb forces, they act in a whole space. So if we are thinking about 3D exciton, electric field, the interaction between electron and hole, depends on the dielectric constants of the material, because the forces act within the whole area. While if you are talking about monolayer, it's different, because most of the field is outside the monolayer. It is in the environment with completely different dielectric properties. So the result can be appreciated here in this slide. If you look at the energy, experimental energy of excited states of an exciton, in a monolayer, you will see that it goes very well outside the simple hydrogen model, which is used in this 3D system. Even 2D hydrogen model, even if you confine your carriers within the layer, but you don't change the dielectric constants, doesn't fit. So in order to explain this, you need to apply another model in which you take into account the dielectric different dielectric constants of a medium which is outside the layer of the material. You need to remember about this. Never-ending story. Just to summarize this part of the presentation, people are discussing very much new possible complexes of electrons and holes, and this really looks like never-ending story. What can we do about those materials more? Just some cases. First, some examples. First, if you think about electrical properties, you can think of changing the the structure of the material. In this case, by changing the structure from 2H to 1P, you get metallic properties, which is very important for electrical applications. Then, by introducing strain, you can introduce single phonon emitters in those materials, which may be important for quantum information applications. Of course, you can alloy your material, changing the band gap and changing the optical properties. You can also create so-called Janus materials, and this is really interesting because you can grow material with different chalcogen atoms layers below and above. Important for application is the robustness of those materials in terms of the strain, and then heterostructures. I would spend just a couple of minutes, and this is the last topic: heterostructures, composing materials of different properties, either vertically or either laterally. Lateral heterostructures, I already told that you can change the properties by changing the structure. But a few comments about what can be done if you put one monolayer at top of the other. You can introduce a completely new story of so-called interlayer excitons. These are this is the photoluminescence from the one material, the other material, and if you create a heterostructure, apparently what you can observe the so-called interlayer exciton, in which electron is mainly in one material and the hole is in the other material. And finally, the idea of so-called moire excitons. Moire potential, what does it mean, moire potential? If you look at the fabric and the two layers of fabric, very tightly woven fabric, sometimes you can see this which we called moire pattern. And this works also for those materials. If you look at the positions of atoms in two layers of TMD, which are put one at top of the other, you can see that depending on the place, that arrangement is different. You can see the moire pattern, moire exciton, moire potential, which localizes excitons. Completely new stories. And finally, just as some sort of touch, quite recently a new chapter of the story appeared, which is the interest of researchers in magnetic materials. For example, those metal phosphor sulfur compound. It's known that can be, depending on the metal, at low temperature it's mostly antiferromagnetic, but then this antiferromagnetism can be of different properties, nil, zigzag, stripy, depending on that terrain. So just some reviews for you to consider if you are after getting more information, and some sort of conclusions. Wide variety of those materials, endless opportunities in terms of creating structures, and that's. And I hope that you some sort of profited from my presentation. I can see that it's already 47 past 11, so it's time for me to finish. Thank you very much for your attention.
Thank you very much for
Thank you very much, Professor Babinski, for this insightful lecture. I think it covered the fundamentals of the research field in 2D materials. We have some questions from the participants. Mr. Kumar asks, what is the phenomenon behind encapsulation that uses exciton energy?
Mm-hmm. Yes, if we think about the energy of an exciton, it is because of electrical interactions, Coulomb interactions. And Coulomb interactions, the Coulomb potential depends on the dielectric constant of the material in which the exciton exists. So if you change the environment, you change the dielectric constant and you change the energy. Of course, there are also another issues, as for example, this roughness of silicon oxide substrate. But I would say mostly this is because of the electrostatics. Yeah.
Mm-hmm. Thank you. We have another question of Mr. Khalid. How can molybdenum disulfide-based heterostructures be integrated with existing photovoltaic technologies, for example, silicon-based cells, to create hybrid or tandem solar cells with improved efficiencies?
This is my personal opinion, but I think that it's very difficult to integrate anything with silicon-based technology. Silicon-based technology is so advanced that, personally, I don't see if this is the very promising direction. I would rather say, why not create tandem cells of TMDs themselves, because you can choose materials of different band gaps, so you can pick some of light. Well, I would be going this direction, but well, I cannot really provide you with a solid answer to this.
If I may comment here, I think next speaker will discuss about integrating 2D materials in perovskite-based solar cells. So I think there is a lot of progress on using 2D materials.
Yes, exactly. Within the tech, yeah. Mm-hmm.
Yes. So I think
within the new materials. Okay. Changing darkish exciton.
Yes.
It is. I can see another. Sorry, another question.
Yes, well, actually, there are a lot of questions. So,
well, about the mechanism, this is about the mixing of bright exciton and dark excitons. Actually, excitons are simply dark. Darkish is material. We call a material darkish because it is not dark. You can see the luminescence, but it is darkish because, well, it is more complicated. But dark excitons can be brightened because of their wave function are mixed with bright excitons in magnetic field applied within the plane. Okay.
Mm-hmm. Thank you. And another question is, what are the effects or defects on the excitons?
Well, normally, if you have any defect, it can localize the excitons. This idea of single phonon emission is really related to the deformation or strain within the layers, which localizes an exciton. So the effect of defect is localization. Yeah, but this is, well, like whole semiconductor physics.
And how can we control the doping of 2D materials? Actually, this is quite...
Yes, this is a very tricky
average
point because there are some ways to dope it. I would say the most reliable is just electric field. But then there are some ways by putting extra atoms. I didn't present the slides about this because of the lack of time. Well, the most effective change of the carrier densities in electrical structures when you just in field defect supplies electrons from outside. Next question is about, of course, we can use whatever substrate we have. This silicon was the first choice because of the method to judge the thickness. You know, this silicon oxide layer allows us to see the flakes under the microscope. But of course, if you think about flexible electronics, you must use flexible substrates. And look, the layers within the structure, the material, are kept by van der Waals interactions, which means that there are actually no covalent bonds between them. This makes it relatively easy to put it on practically every substrate because they don't form any tough bonds with the substrate.
Is there any other question? I think Irene will cover more.
How can we explain the darkish exciton behavior in different domains, vacancy domains?
To move forward to our next speaker.
Well, I would say domains have different potential. Okay, but I understand that in most cases we are referring to the situation with no vacancies. So this darkish exciton behavior is related to just, I would say, ideal case with no vacancies. So I can't really comment on what's going on if how those domains enter. Well, sorry.
Okay, I think you covered all the questions from the chat. I think now we have to proceed to the next speaker. So we'd like to thank you very much for your participation, Professor Babinski.
Thank you very much. It's my pleasure.
It was a very nice introduction to the field. So I'm checking the chat. Some people asking about the Moodle test. This will be done after we finish the whole series of webinars this week. So then we will open a Moodle test, a Moodle account. All the slides from each presenter will be uploaded there. We also try to upload also the recording, all the videos for the presentations. Then you will have some time to study all the material. And after, let's say, some weeks, we will set